All right. In the last class, we considered or we figured out what the properties of the function f of omega must be in order to be able to shift the characteristic from, in other words, transform the ideal low pass filter characteristic to other characteristics that we might want to realize in practice, like the band pass, the band stop, and the high pass. Today, we will continue with the study and try to realize or transform the ideal low pass filter prototype into a response which is periodic. Okay, and the basic idea what we want is this. So this is the ideal low pass response. Let's say the cutoff frequency was 0, and let's say you want to realize a periodic response of this nature. To infinity. Okay, and just to make the algebra less messy, I will choose this to be say pi 2 pi blah blah blah. So 0 in the prototype must map to 0 plus minus pi plus minus 2 pi and so on. In general, plus minus k times pi, where k is an integer, right? And from our study of the properties of f of omega, we realize that f of omega is the reactance of an ideal LC lossless network. So zeros and poles must be interlaced. So let me quite arbitrarily choose these points to be the middle of the pass bands. In other words, what must map to pi by 2, 3 pi by 2 and so on? Infinity in the low pass prototype must map to pi by 2 plus minus, or rather plus minus pi by 2 plus minus 3 pi by 2 and so on. In other words, it is plus minus k pi plus pi by 2. Okay, there this is correct. So f of omega must therefore have zeros at integral multiples of pi and must have poles at plus minus pi by 2, plus minus 3 pi by 2 and so on. Clear? Okay, so f of omega must be of the form some constant k. Oh no, I'm sorry, no, I can't use k, I've got to use some other name. Let me call this, I don't know, L. Okay, and omega times omega square minus pi square into omega square minus 4 pi square blah 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 divided by omega square minus pi by 2 whole square into omega square minus 3 pi by 2 whole square blah blah blah. Okay, and by the discussion we had the last time around, we realized that when you have a lossless LC impedance, its poles and zeros must lie on the j omega axis, which means that the only thing relating this to f of omega, this must be a factor. The only other thing possible is a constant. You cannot have any other term which goes to 0 other than on the j omega axis. Now one could write this in a slightly different way. which we call this say L1 into omega times 1 minus omega square by pi square times 1 minus omega square by 4 pi square to 1 minus omega square by k pi whole square divided by 1 minus omega square by pi by 2 whole square times 1 minus omega square by 3 pi by 2 whole square and so on. 1 minus omega square divided by k pi plus pi by 2 the whole square. Does it make sense? Now, if you think about this, you see that this function goes to 0 at 0, pi, 2 pi, minus pi, minus 2 pi and so on to infinity, and it is an odd function of omega. The numerator is an odd function of omega. Are you able to see that? Okay, so how will it look like? It must go like this, must come back like this, like this, like this, like this and so on. Okay. So it turns out, and it is not unreasonable, that this is nothing but the product expansion of sine. So pi of omega times 1 minus omega square by k square pi square, k equal to 1 to infinity, just turns out to be sine omega. This is the product form expansion of a sine wave. Okay. Similarly, pi k equal to 1 to infinity, 1 minus omega square by k pi plus pi by 2 the whole square must be equal to cos omega. All right, and you can see this kind of at least passes sanity check. As omega tends to 0, what happens to this character? I mean, as omega, when omega is 0, it is 0, but as omega tends to 0, what is it? It goes as omega, right? And that is definitely also the behavior of sine omega. I mean, just because you know the roots doesn't mean that you know the whole polynomial, right? You only know it to within a constant, right? To find that constant, you have to use either a point somewhere or the slope somewhere or something to that effect. Similarly, this also passes sanity check at small omega. This is the form, 1 minus omega square by what is this now? Have I made a mistake somewhere or what? What is the transformation? Omega must therefore go to, what should you replace omega by? Not tan omega, there is some constant L1 times tan omega, okay, and which means j omega must be replaced by j L1 tan omega, which means S must be replaced by j L1 tan of S by j, which is L1 tan hyperbolic S. Okay. Right. I mean, if you're not comfortable with tan of a complex number, you just go. I mean, it just comes with familiarity. You just expand this as cos by sin, I mean sin by cos, and then do e to the j argument plus e to the minus j argument by 2j and all this stuff, and you will end up with L1 tan hyperbolic S. So, what do we notice? Yeah, so the bottom line is that the appearance of tan hyperbolic, which is a transcendental function, means that distributed circuits are involved. Before I go there, let me just quickly discuss how you choose L1. How would you choose L1? So, of course, the slope must be positive, so L1 must be a positive constant. What else? We still haven't figured out what 1 maps to in the prototype. We just said DC maps to 0, pi, 2 pi and so on, and we have said infinity maps to pi by 2, 3 by 2, 3 pi by 2 and so on, right. So, let us say this maps to omega 1, okay. Then you use this information. So, 1 omega maps to L1 tan omega. So, in other words, if you want 1 to map to L1 tan, what is this, omega, what do we call that, omega 1, which means that L1 is 1 by tan omega 1. So, in other words, S must map to tan hyperbolic S divided by tan of omega 1. Okay. Now, if you didn't want this to map to, you didn't want to repeat at this response to repeat at pi, 2 pi and so on, but at omega naught, 2 omega naught and so on, what would you do? Okay, sorry. So, it's S pi by omega naught. Okay. All right. So, now we need to figure out what will happen to the network. So, in the prototype you had Ls. What must happen to it now? Must become L1 tan hyperbolic S pi by omega naught. Correct? It's just matter of replacing S with this other expression that we got for f of omega, which happens to be L1 tan hyperbolic S pi by omega naught. Okay. Alright, so now we might be, I mean, this is clearly not an inductor, we'd like to figure out what this element is. And it happens to be a transmission line. Let me quickly cover some basics of transmission lines. A transmission line is basically characterized by two numbers. One is the characteristic impedance and the other is the length, which is equivalent to saying how long a wave travels from one side to, how long it takes for a wave to travel from one side to another, right. So, we call that time. Okay. Now, depending on the velocity of the wave in the medium, the tau will, the tau can change even though the physical length is the same. So, if you know the length and the velocity, then time is nothing but length by velocity. All right. Now, the any voltage or current on the transmission line can be represented as the sum of a wave going this way and a wave going the opposite way. So, at any point on the line, the voltage, absolute voltage V, can be represented as V plus at that point in the line plus V minus. V plus is a wave traveling this way, and this is the amplitude of a wave traveling in the opposite direction. Right? In the same manner, the current, if I basically take a saw and cut a transmission line through, right, the current at that point will be simply V plus by Z naught minus V minus by Z naught. Z naught is a characteristic impedance. So, you can basically associate the voltage and current at any point in a transmission line as being comprised of the superposition due to the effects of two waves, one wave which is traveling this way and the other wave which is traveling the opposite way. The voltage is simply the sum of the amplitudes of the two waves. The current, physically it seems apparent that if a wave is traveling this way, it is probably associated with the current going this way, and a backward traveling wave is associated with the current in the opposite direction. The actual current, the real current at that point is simply the sum of this current plus this current, which means that it's algebraically the difference. Okay, is that clear? Now, this is true for any point on the wave, on the transmission line. Now, what actually happens is at some other point on the line. So, let's say I know the amplitude of the forward, and if I know the waves at this point, what do you think? And this and this time or this length corresponded to a time of tau 1, what do you think the forward and backward waves here are in terms of the Laplace transforms? Do you understand the question? The question is that at this point I know that the forward and backward traveling waves are V plus and V minus, which are some functions of time. Okay. Because if I saw through the transmission line and put a voltmeter or ammeter at that point, the voltage will be a function of time, correct? Okay. So, if I know the functions of time of V plus and V minus at some point, okay, and if I am interested in finding V plus and V minus distance tau 1 away, what do you think they will be? Very good. V plus will be advanced, right, and V minus will be delayed. So, in other words, the V plus in terms of Laplace transforms, if it is advanced, what do you think it will be? E to the plus s tau 1, and the reflected wave or the backward traveling wave will be V minus e to the minus s tau. Okay. And correspondingly, what will the current be? It will be V plus e to the s tau 1 by z naught minus V minus e to the minus s tau 1 by z naught. Okay. All right. Now, let us understand what happens to a transmission line under various simple conditions. So let's say, you understand that a transmission line got to have, has two conductors, right? One is the outer conductor, one is the inner conductor, and the electric field is established between both these conductors, and then there is a magnetic field between the two conductors. So you can basically, physically, you can think of it as a coaxial cable if you are if you want to associate something physical with it. Now, if the far end of the line is shorted, let's say this is Z0 and tau, what can you say about the absolute potential at this node? It's got to be 0. If the absolute potential is 0, what do you think is V plus in relation to V minus? All that we can say is the sum of the wave traveling this side and and the wave traveling backwards is identically 0. So all that one can say is that V minus must be minus of V plus. Okay. Now if this is minus of V plus, what happens here? What happens when this reflected wave gets to the input? This is V minus e to the minus s tau, which is the same as minus V plus e to the minus s tau. Correct? And what must be the forward going wave here? V plus e to the s tau. So if I slice the transmission line at that point, what is the absolute voltage? What is the absolute voltage? V plus into e to the s tau minus e to the minus s tau. Correct? How about I in? No? I in is nothing but V plus e to the s tau by z naught, okay, minus V plus e to the minus s tau by z naught. That makes sense? The reverse going wave has an amplitude of is minus V plus e to the minus s tau, but that's going this way, so the current must be going in the opposite. So this must be V plus by z naught into e to the s tau plus e to the minus s tau. Does it make sense? All right. Now, so what is the input impedance? Z in? Z naught tan hyperbolic s tau. Okay. Understand? Okay. Now, going by the same token, if this end of the transmission line was open, what can you say about V plus and V minus at the right end of the line? The current is 0 because it's an open circuit, which means that V plus must be equal to V minus. So this must be V plus e to the minus s tau. This must be V plus e to the plus s tau. So V in is V plus into e to the s tau plus e to the minus S tau, whereas I in is V plus by Z naught e to the S tau minus e to the minus S tau, which means Z in is Z naught cot hyperbolic S tau. Does that make sense? Okay. So let's it's instructive to see what happens to the impedance. So Z in is Z naught cot hyperbolic S tau at low frequencies. How does cot hyperbolic behave? 1 by, look carefully, 1 by S tau, correct? It's 1 by tan hyperbolic. Tan hyperbolic is the same as the argument at for small values of the argument. So this is true. So Z in is approximately at low frequencies is Z naught by tau times S, correct? And what is this now? This is a capacitor of value tau by Z naught. You understand? Similarly, if you evaluate this at low frequency, what do you get? At low frequencies, approximately Z naught times tau times S. Okay. So this looks like an inductor of value. All right. So in other words, if you took a general transmission line, a good approximation to this at low frequencies is this. You understand? It makes sense because if I short this, I must get, I short this in the equivalent circuit and I must get Z naught times tau. If I open circuit this, right, this becomes a short at low frequency, okay, and I get tau by Z naught. All right. So this is a first order approximation for a transmission line. It's a very useful result, as I'll demonstrate in a couple of minutes. Okay. By the way, this S going to L1 tan hyperbolic pi S by omega naught is what is called the Richards transformation. Okay, and is a technique for transforming a low pass filter prototype to a filter which has got periodic response. Okay. All right. Now, as we saw, an inductance of S times L will become will become an impedance of a box whose impedance is L1 tan hyperbolic pi s by omega naught. Similarly, a capacitor will become an element whose admittance L1 tan hyperbolic pi s by omega naught. Oh, sorry, I'm sorry. L1 times L and L1 times C. Okay, which can be realized using transmission line elements. And I'll leave the details to you as an exercise. Okay. I've already discussed what an open circuit line and what a short circuit line does. So based on that, you should be able to go and figure out what you should do in the prototype LC network. Okay, is that clear? Okay. Now, the next thing, therefore, so a couple of comments on this. If you have a periodic response in the frequency domain, it must follow that you will have impulses in the time domain. Okay. And similarly, if you have and this makes sense because you have only, you've already seen that an inductor is nothing but a short circuited transmission line and a capacitor is an open circuited transmission line. So when you keep bouncing an impulse, it keeps like hitting open circuits or short circuits, coming back, going through the network and coming out. So finally you must see a sequence of impulses. In other words, if you plot the step response, it must look like a sequence of steps. Okay. So let me just, so I leave this to you as an exercise to figure out the details of the transmission line length and all this. Once you're given the formula and once you're able to relate the open circuit and short circuit impedances of a line, you should be able to figure out, given omega naught, you should be able to figure out what length of transmission lines you must use and so on. And then when you run a simulation, you will find that indeed the step response looks like a sequence of steps. Okay. A couple of minor points that I wish to make regarding these frequency transformations. Let's say you had a network with only R's, capacitors and control sources. And control sources of the following type: VC, VS and CC, CS. You don't know how the elements are arranged inside. You just know that there are resistors, capacitors, control sources of these two types, and you also know that you have a filter which is a low pass filter. Okay. Now you would like to transform it into you want to use this as a prototype and transform it into a high pass filter. What do you think you will do? What would you do? Based on your prior knowledge, what will you do? So the low pass to high pass transformation is saying that S must be replaced by omega naught by S. In other words, SC must be replaced by omega naught C by S. In other words, every capacitor of value C must be replaced by an inductor of value 1 by omega naught c. Correct? So, in other words, if you want to make this a high pass filter, what do you think will happen to the resistors? Remain the same because they don't contain any S term. What do you think will happen to the controlled sources? They are all dimensionless, correct? So, they have nothing with frequency inside. So, okay, so they will remain the same. Now, to get a high pass network, what we have the same R, same VCVS, CCCS, okay, except that instead of the C, you have an L which is 1 by omega naught C. In other words, the rule is replace every capacitor in the original network by an inductor of value 1 by omega naught C. So, now this high pass network that you have will contain only resistors, inductors and control sources. Okay. Now, the question is there something I can do to get rid of the inductors? Correct? What do you think I should do? So, if you now wanted to avoid inductors in the high pass network, so please note that this network consists of only resistors, inductors and controlled sources. And if you want the same transfer function as this network, okay, one way of doing this would be to scale all impedances by the same factor. All of you realize that if you take a network and scale all impedances by the same factor, no transfer function can change because the transfer function is dimensionless. Okay. So, a way of realizing the same transfer function as this box is to scale all things in the box with dimensions of impedance by a factor R by, scale them by factor S. So, if the original inductor, the original impedance of the inductors would be S by omega naught C, this times 1 by S, and the control sources would stay as they are. So, this becomes a capacitor and this becomes a resistor. Does that make sense? Okay. So, if you look at this network, and this character, you see that resistors have become capacitors and capacitors have become resistors. So, this is often called the RCCR transformation. And a simple example is the following. Let us say this is 1 ohm and this is 1 farad. The transfer function is 1 by 1 plus S. If I want to make this a high pass network, I should replace S with 1 by S, correct? And so, what I will get is I must replace this by 1 Henry inductor and 1 ohm. And what is the transfer function here? S by 1 plus S. Now, if I scale all elements, all impedances in this network by S, what will I get? If I divide by S, I will get 1 by S. Let me draw the capacitor right away. And this is also S by 1 plus S. So, this is impedance scaling by does it make sense? Okay. So, what we see is that every resistor has become a capacitor, and every resistor, if I now just don't show this at all, every resistor has become a capacitor and every capacitor has become a resistor. Does it make sense? Okay. All right. So, this is one thing that I want to mention. The next thing I wanted to show was all of you will recall that the general kind of specs that one is used to for a low pass filter are the following. We all agree that the DC gain must be 1, okay, and at omega 1 mod H must be greater than A1, and at omega 2 mod H must be less than A2, right? And then you decide on your favorite approximation, Butterworth, Chebyshev, Inverse Chebyshev, whatever, and you plug in the appropriate formula and you will get an expression for both. You will be able to solve that for order as well as the cutoff frequency, correct? You remember or no? Yeah. So, and of course, there is no unique solution. If you go on increasing the order, the cutoff frequency can vary all the way between omega 1 and omega 2. If on the other hand, obviously in engineering practice, it makes sense to realize a filter with the least possible complexity, in which case one would typically choose the lowest order that would meet spec. Okay. Now, the question is, what happens in a band pass case? And the same thing, will also hold for high pass and band stop and so on. I will just cover the band pass example. So, in the band pass case, again, you say at some frequency you want the gain to be close to 1. At some frequency omega 1, omega 2, okay, you want the gain to be greater than A1, and at some frequencies omega 3 and omega 4, you want the gain to be less than A2. So, a legal characteristic or a characteristic you might be happy with is something like this. Okay. So, how do you think we would go about finding the order of the filter required? Let us think back to what we did in the low pass example. What did we do first? So first thing to do is to choose whatever approximation you want. You choose your favorite, Butterworth, Chebyshev, Inverse Chebyshev. You pick one of them, and then at least you know what formula to use. Okay. So now, the first step is pick the approximation. All right. Now, what next? Okay, there are two ways of going about it. One is to say, hey, I know the expression for the response of the band pass filter. What is that? I know the expression for the low pass filter, and what would be that expression? So we need to find what do you call? We need to find. You replace omega in the low pass filter prototype with q times whatever s in the low pass filter prototype with q times s by omega naught plus omega naught by s. At this point we don't know anything, right? We don't know the order, we don't know omega naught, we don't know q. Correct? Okay, so the first thing to do is to figure out what approximation you want to use. Then we say, okay, one thing we could do is say plop this q times omega by omega naught minus omega naught by omega instead of omega in the low pass filter expression, and you will now get this huge polynomial, correct, which you need to deal with, and then you can go and do the math. Okay, it gets very messy. An alternate way is to do the following: instead of converting the response from low pass to band pass and then manipulating the stuff, you can convert the spec from a band pass spec to an equivalent low pass spec. You understand? Both are equivalent ways of doing it. The latter is a lot more efficient way of doing it. So convert the band pass specs to low pass specs. And how might one do this? One thing to bear in mind is that if 2 points have the same amplitude, if if you have a low pass filter and you perform the low pass to band pass transformation, one frequency in the low pass will transform to two frequencies in the band pass. And what are the two frequencies? What is so special about the two frequencies? They will be geometrically symmetric about omega naught. Okay. So in other words, since we want the spec to be in such a way that this amplitude and this amplitude limits are the same, right? We can form the product omega 1, omega 2, okay, and the product omega 3 and omega 4. Omega 1 and omega 2 are geometrically symmetric about omega naught, okay, and omega 3 and omega 4 are also symmetric about omega naught, but this omega naught and that omega naught need not be the same. I gave you, the spec is some random omega 1, omega 2, omega 3, omega 4. It does not mean that the spec will be such that omega 1, omega 2 will be equal to omega 3, omega 4. So there are three possibilities. The first possibility is that omega 1, omega 2 equal to omega 3, omega 4, in which case what do? When you are happy, all that you need to do is you equate this to omega naught square, and you have found your omega naught. Correct? On the other hand, if omega 1, omega 2 is greater than omega 3, omega 4, what will you do? If finally you want to make omega 1, omega 2 equal to omega 3, omega 4. You want to make the two products the same because the response is the same for both those frequencies. If something is larger than something else, if you want to make the two equal, what will you do? One thing to do is you either reduce this or you increase this. Okay. So if I decide to reduce omega 1, omega 2, what do you think I could do? To reduce the omega 1, omega 2 product, what could I do? I could either reduce omega 1 or reduce omega 2 or reduce both. What do you think is the most sane choice? Reduce omega 1. Why not reduce omega 2? The spec will be violated. So the same thing to do is to either reduce omega 1, in which case the spec will be now, what do you call is that it's now a tighter spec for omega 1. In other words, if you increase omega 1, what happens is that this window probably comes somewhere there. Okay. If you reduce omega 1, that's what will happen. Okay. All right. Alternately, or if you wanted to increase omega 3, omega 4, which will you increase? Increase omega 4 or decrease omega or increase omega 3? Increase omega 3, correct? If you increase omega 4, what will happen? Let's say you increase omega 4 like this, and then what you will get will be something like that. It will not satisfy the spec. Okay. Similarly, if omega 1, omega 2, so that omega 1, omega 2, yes, or reduce omega 3, increase omega 3, right. So finally, omega 1, omega 2 must be the same as omega 3, omega 4. Okay, and this must be equal to omega naught square. Okay. Now on the other hand, if omega 1, omega 2 is smaller than omega 3, omega 4, what all could you do? You could increase omega 1, omega 2, and what will you do? You will choose to increase omega 2 or reduce omega 4, so that again omega 1, omega 2 equals omega 3, omega 4, which is equal to omega naught square. Does make sense? So at the end of this step, you now have a situation where omega 1, omega 2 is the same as omega 3, omega 4, which means that both omega 1 and omega 2 will map on to some omega LP1, okay, which corresponds to a frequency in the low pass prototype. Omega 1 and omega 2 are both geometrically symmetric about omega naught. Okay, so they will transform to the same frequency in the low pass prototype. Does it make sense? Similarly, omega 3 and omega 4 will transform to omega LP2. Okay. So in effect, now you have a low pass filter spec which has got an amplitude limit or a limit on the response at omega LP1, a limit on the response at omega LP2, okay, and you already chosen the approximation, your favorite, Butterworth, Chebyshev, whatever, from which you can go and find the order as well as the cutoff frequency. Okay, and so once you find the order for the low pass, what do you think you will get for the band pass order? Double the order, and I mean, once you figure out the order and the transformation is basically figured out, you will have the entire transformation and you can fix the hole. Okay, all right. So this is a way of, I mean, and you can do the same thing whether it's a low pass, high pass, I mean whatever, whether it's a high pass, a band stop or a band pass. The key is to simplify matters by, instead of transforming the response from low pass to band pass and then trying to fiddle around with those numbers in order to meet the spec, an easier thing is to transform the spec to an equivalent low pass spec, do everything in the low pass domain, and finally probably even synthesize it in the low pass domain, and then finally do the low pass to band pass transformation on the network elements, right? There is no need to find h of s for the band pass filter, you will get a huge expression, right? What you finally are interested in is the network. So you transform the specs to a low pass spec, synthesize the low pass network, then replace the elements element by element. If you do a low pass to band pass, every L becomes a series LC network and every capacitance becomes a shunt LC. You understand? And so on. Okay?
Converting back to the low pass case.
Yes.
So it's isn't it the cutoff frequency already fixed as 1?
Yes, that's correct. That's fine. Omega LP1 and omega LP2 will be such that omega LP1 will be smaller than omega LP2. You understand? Okay. and one will be smaller than the other. So I mean, and you just need to find the what do you call? So there are two variables to find. Correct? There is order n and there is the Q of the transformation. All right. So you just plug it in and then. So there's a problem in your assignment on this stuff. So I think with this.